Heavy fuel oil meters are designed to run reliably under standard industrial pressures. But when a mechanical system reaches its limits, the failure is immediate. This heavy flanged pipe connection ruptured without warning, violently ejecting viscous black fluid. Prior to the shutdown, this specific meter had been operating continuously for 4 years. The fluid temperature held steady between 56 and 62 degrees Celsius, with standard low-pressure operating parameters of 40 to 60 psi. This post-shutdown photograph reveals the primary forensic anomaly, an unbroken sequence of 8 heavy-duty bolts fractured along the bottom edge, positions 1 through 8. Consequently, the internal seal was destroyed, with the rubber O-ring and gasket extruding from the joint. These are the actual severed fasteners recovered from the site. They are 3/4-inch, grade 5 high-strength steel bolts. Hardware of this caliber possesses a tensile strength designed to handle loads vastly exceeding a 60 psi operating pressure. 8 of these high-strength components snapping in a contiguous row points away from a localized material defect. It indicates a massive failure in how the mechanical load was distributed across the joint. This photograph documents a second, distinct set of hardware recovered from the exact same flange. 3 intact but severely deformed fasteners were pulled from the 12, 8, and 4 o'clock positions. The head markings on these deformed bolts reveal they are ASTM A307B standards. They belong to a completely different, lower-grade material specification than the grade 5 bolts at the bottom. The physical evidence presents an immediate mechanical contradiction. High-strength steel fasteners snapped cleanly across their diameters, while softer, out-of-spec bolts in the same assembly yielded and bent without breaking. The grade 5 bolts fractured when human error at the time of assembly intersected with a precise geometric vulnerability in the joint design. To trace that sequence of events, we have to look past the macroscopic damage. Rebuilding the exact stress state at the moment of failure requires deconstructing the fracture mechanics down to the microscopic level. Before analyzing the mechanics, we must eliminate variables in the steel itself. We need to confirm whether improper heat treatment or a bad material batch compromised the fastener metallurgy. This micrograph shows the crystalline structure of the broken grade 5 fasteners. The presence of scattered white patches of bainite within the dark tempered martensite confirms the steel was properly heat treated to specification. Comparing this to a cross-section of the bent bolts, we see a distinct directional ferritic-perlitic grain structure. This confirms they behave exactly as softer A307B standards should. Independent hardness testing and chemical analyses further verified that ball hardware met exact SAE and ASTM specifications. The metallurgy is sound. The steel performed exactly to its rating, meaning the forces that tore these bolts apart were overwhelmingly mechanical. Looking directly at the macroscopic fracture surface of one of the broken bolts, the dashed red line separates 2 distinct topographies, a relatively smooth, flat fatigue zone and a rough, granular region of final, sudden rupture. The presence of a fatigue zone, marked by the band of coarse striations mapping the direction of crack propagation, identifies the exact failure mechanism. This is a premature, high-stress fatigue fracture. Zooming in on the precise edge where the crack initiated, the yellow arrows highlight numerous microscopic ridges known as ratchet marks. Ratchet marks form when multiple stress fractures spark simultaneously along a harsh geometric boundary, in this case, the root of the thread. These individual cracks compete and propagate inward before coalescing into one massive crack front. This multi-point initiation is driven by the stress concentration factor, or KT. This is a geometric multiplier. When tension flows through a part, sharp notches like bolt threads trap and drastically spike the localized force. The sheer density of ratchet marks proves that high stress concentrations across the entire thread root triggered simultaneous fatigue initiation. This photograph aligns the severed bolt shanks to show precisely where that stress hit its peak. All 8 catastrophic fractures initiated at the exact same axial location, right where the threads end. That specific location is the thread runout. It is the transitional zone where the depth of the machined thread fades out into the solid diameter of the shank, a physical feature that inherently carries a high stress concentration. This animation plots the exact physical location of that runout relative to the assembled heavy flanges. When the bolt is inserted and clamped down, the glowing red marker indicates that the highest point of stress aligns perfectly flush with the microscopic gap between the two flange faces. Positioning a stress razor exactly at the joint interface is highly volatile. If the flange faces separate even slightly on one side, they act as a fulcrum.
The mechanical bending force focuses entirely onto that singular geometric point at the runout. The design itself laid the trap. The runout alignment created a vulnerability that only required an uneven operational load to snap the bolts. The relative sizes of the smooth fatigue zone and the rough final fracture zone on a broken surface act as a permanent historical record. They tell us exactly how the load was distributed when the part failed. Here we have the array of all 8 fractured bolt faces, laid out sequentially from position 1 through 8. The dashed yellow lines separate the slow fatigue growth from the fast final fracture. Focusing on panel E, which corresponds to bolt 5 at the dead center 6 o'clock position, the smooth fatigue area is massive. The crack had to travel almost completely through the bolt before the remaining steel finally gave way, proving this position experienced the lowest relative stress. Tracing the pattern outward toward the edges, across panels D, C, B, and A, the dashed yellow line drops progressively lower. The final fast fracture zones grow significantly larger the further you move from the center. This reveals that the mechanical load on the joint was heavily non-uniform. The stress distribution formed a distinct U-shape, peaking at the outer edges, a pattern completely inconsistent with the even outward push of a standard pressurized seal. Fracture mechanics literature has often assumed that the curvature of a fatigue crack front is strictly dictated by the raw amplitude of the overall mean stress, expecting higher stress to yield a distinct crescent shape. We can test that assumption by comparing panel A, the highest stressed bolt on the flange, against panel C, a moderately stressed one. Notice how the crack front on the highly stressed bolt is perfectly flat, while the lower stressed bolt exhibits a crescent curved shape. The helical geometry of the threads dictates the fracture morphology, overriding the influence of simple axial force. This 3D model demonstrates the reality of thread architecture. As a flat crack propagates horizontally through the steel, its outer edges inevitably strike the spiraling thread root. Because a thread descends rather than forming a flat ring, the crack edges hit physical ridges, forcing them to drag and slow down while the center races ahead, bowing the plane into a deep curve. The crack front will remain flat only until its edges strike this geometric misalignment. The moment it hits the ridge, the local stress field shifts, and the fracture is forced to curve. The varying crack morphologies across these 8 bolts are a dynamic reaction to physical geometry and crack length, not merely a static read of load. It highlights the intricate interplay between component design and the path of failure. Returning to the macro scale, we must explain the severe U-shaped load distribution that tore through the bottom fasteners while leaving the top bolts intact. The missing variable is load eccentricity. This occurs when massive bending moments are introduced into a mechanical system that was engineered to operate strictly under linear clamping tension. This diagram maps out the fatal sequence. To manage the heavy, awkward weight of the meter assembly, technicians took a shortcut. They used 3 softer, out-of-spec bolts at the top, 12, 8, and 4 o'clock holes, simply to pin the rig in place, allowing the entire top half to act as a loose hinge. That single procedural choice threw the entire assembly out of parallel. The massive flange faces were left hanging at an angle, creating a wedge-shaped gap down toward the bottom 8 positions. Tightening the bottom row of bolts forced the thick steel flanges to bend closed against their own rigid geometry. This negligent, non-parallel assembly turned the rigid steel of the flange into a massive crowbar, leveraging immense prying force directly against the lower fasteners. This cross-section illustrates the severe bending forces generated by that assembly error, intersecting directly with the system's geometric flaw. While the fastener attempts to hold linear tension, a massive perpendicular bending vector pushes hard from the side, combining perfectly at the thread runout. The mathematics of this interaction are lethal. The geometric multiplier of the thread runout, compounded by the extreme bending eccentricity from the crowbar effect, spiked local stresses far past the grade 5 steel's yield point. Once localized yielding compromised the thread roots, the normal cyclic pressure variations of the fluid line took over. The microcracks formed, competed, and rapidly propagated through the shanks via fatigue. The overarching engineering lesson here is absolute. Specifying high-strength materials cannot mathematically overcome poor procedural torque patterns and non-parallel joint closure. In industrial mechanics, reliable systems demand both precise geometric design and rigorous assembly protocols. Without one, the other is merely waiting to fracture.